Okay.
Get happy.
Oh, cheese and crackers. Okay.
Keep going.
Ionization is energy required to move the outermost electron from the gaseous atom, the nucleus of that gaseous atom. And when enough energy is added to the atom of the outermost electron, it can use that energy to pull away from the nucleus completely, and in the process, it leaves behind a positively charged ion. What are you doing?
He hit me right here.
You sound like a big baby. Anyway.
That is not. We'll just start all over.
Next, the closer and more tightly bound an electron is to the nucleus, the more difficult it will be to remove, and the higher its ionization energy will be. And this is where my partner, Efrain, takes over. Ta-da! Take it away, Efrain.
Hey, Ms. Aarons. To get rid of an electron, I'm going to mess up a couple times, Ms. Aarons. I'm sorry. But from here is a low to high. The noble gases don't matter, right, Jesse? Because they already have 8 electrons in their atom shell.
Happy.
They're happy. Happy. Here, they're only trying to get rid of 1 electron. 1, 2, 3, 4, 5, 6, and 7. And that's where it stops. The thing that people don't know is that if you're trying to get rid of an electron and you say, what's harder to get rid of an electron? What's this one? No, I'm going to use, I hate when this does that. I'm going to use potassium or nitrogen. What's easier to get rid of? Most people would say nitrogen because, it's 7, right? Wrong. It is actually potassium, because potassium only has to get rid of 1 electron. Nitrogen has to get rid of 5. 1. Big difference, Miss Aarons. No, we're not. You're going to cut that out again. To the next slide. As you can see, the ionization...
Yeah, IE is short for ionization.
IE is short for ionization energy. The IE and atomic size number is increase. As you can see, the IE and the atomic size increase in opposite directions. Challenge question for you, Miss Aarons.
Make sure you're paying attention.
Make sure you're paying attention. Can you make this finger and this finger go opposite directions? Oh, I can do this. I don't think you. Oh, no, I messed up. I don't think you can do that, Miss Aarons. All right. Anyways, this should make sense because as the atoms get smaller, the valence electrons become closer to the nucleus, which is true. Obviously, it's true. This means the attractive force holding the electron is stronger, and it takes more energy to pull the electrons off. So you want to? If you count, remember how there's 2 electrons, and then it goes to 8, and then 8 again, and then it goes to 16, right? But in the potassium, there's only 1 electron in the outermost shell, right? So it's easier to get rid of 1 electron than... Let's go to the next slide. So if you look at the picture... I feel stupid saying. I feel stupid talking. Alright, if you look at the picture, there's only 1 electron in the outermost shell. If you look at the nitrogen one, there's 5. It's easier to get rid of 1 electron than it is to get rid of 5. So, yeah. So I'm just gonna send it over to Jesse right now. So, see you later, Miss Aarons and students.
Alright guys, this is Jesse bringing you the next part in our amazing adventure in learning about ionization energy. Now, we already know about potassium, how it wants to get rid of an electron, so it has a low ionization energy, unlike something like nitrogen, which has 5 electrons and really wants to get one, so it has a high ionization energy, meaning that it would be hard to take away an electron, but more easier to add one. Alright, so adding on to what Efrain said, it'd be easier to get rid of an electron from, let's say, potassium then it would be to get rid of an electron from nitrogen. So yeah. And so what about like noble gases, right? Or these guys that are just chilling. So these guys really don't want to get rid of their electrons. They're at their happy state. I mean, let's take neon for example. And neon's like, hey man, I'm happy. I have 10 electrons. I'm good. Don't mess with me. So it would take a high amount of energy in order to take away an electron from it. Unlike lithium here, where it needs a low ionization energy in order to take away an electron, so it can be happy, because that's where we get to where it's stable. But actually, as we go down, the electron cloud is much bigger. So cesium has 55 electrons. So it really wants to get rid of an electron, just as lithium. But it's actually gonna take less ionization energy than it would lithium to take away that electron, because the electrons are getting farther and farther away from the nucleus. And kind of like xenon here, even though it is happy and all, it wouldn't take as much energy as it would neon in order to take away an electron. So it's more willing to give it away. Alright, so with that being said, let's move on. So here we have hydrogen, and hydrogen has a charge of about 13.5 electron volts. So, and then we have helium, which is almost double that. So when you add one more to helium, the ionization energy decreases, and we go back down here and to the next element, which is lithium. And so now lithium, it takes about 5 electron volts to take away lithium's 1 electron that it wants to give away, to bring it back to helium, so it can be happy. And then we continue to go up again, up until we get to neon. And then when we add one more to that, again we get sodium. So now sodium wants to get rid of that electron. And you start to see this, and it's a pattern, because sodium is just a little bit lower than lithium. And so, like we said before, as the electron cloud gets further and further away from the nucleus, it doesn't take that much energy to take away an electron from it. But as it's closer, it gets a lot harder. That's for noble gas. For noble gases as well, you start to see this pattern as it goes down, and same through here. And so it's easier to take away an electron as we go farther and farther down the periodic table. The same goes for the noble gases, because for here we have the S and P blocks, and then we start going to the D blocks right here, and then F blocks to fill in, which we won't do right now. So yeah. Alright, so just to review about anything, almost. Ions are protons that don't equal electrons, for those of you who didn't know, which shouldn't be anyone. So an example, like hydrogen, and you take away an electron, so then you have hydrogen plus an electron. So this is going to have a positive charge and -1 charge. So this makes a cation, and so if you were to do it the opposite, you'd have an anion. And an easy way to remember that is just, cations have a positive charge. Yeah. So that an easy way, just in case you can't remember, in case it's on the test, but it's a good way. Alright, so real quickly, I'm going to show you how to calculate ion energies. Here we go. Okay, so first, you have to identify the Z for the atom. You have to identify the value of Z, which is the atomic number. So, it appears above the symbol for the atom. Like I said, the atomic number, for example, the Z equals 1 for hydrogen. So, step number 2, you got to decide how many electrons the atom contains. And the number is the same as the atomic number unless the atom has already lost electrons, gained, then that's different. So, you have to calculate the ionization energy in units of electron volts, eV. So, for a 1 electron atom, by squaring Z and then multiplying that result by 13.6. Okay, so then step number 4. For atoms with more than 1 electron, you have to arrive at the ionization energy in units of electron burst. First, by subtracting 1 from Z of whatever the atomic number is, squaring the answer, and then multiplying 13.6 to get your result. Alright, so the last things I want to talk about, the ionization energy of an atom, it's equal to the amount of energy given off when an electron is added to an atom. And so we call that energy that's given off electron affinity. So ionization energy is equal to electron affinity. So for most atoms, the electron affinity is exothermic, which means that there's energy that is given off. But for those that are energy is given by a source, then that's endothermic. So to review, we've talked about what is ionization energy, and that's just required to remove the outermost electron from gaseous atoms. And we talked about how, for the most part, the elements in the S blocks, such as these guys, they really want to lose an electron to become stable, like these noble gases right here. And so, but unlike these guys, all these noble gases, they won't want to give up their electrons quite as easily. But in comparison, like radon is more willing to give up an electron as much as neon, which really wants to keep its electron because it's happy. So, and we've talked about how going down, yes, they get weaker and weaker. The ionization energy gets weaker. And talking more about it and how showing you examples and all, and talking about how what are ions and cations, and a new fancy way of remembering that. Talked about the graphs and how they trend from lithium or from hydrogen right here and going to helium, which is about double the electron volts. So then when you add an electron to that, you get back to lithium and the ionization energy decreases. So, and talking a little bit about how to calculate that. So that's about it. And so this is Jesse, Ephraim, Capril, and Elizabeth bringing to you this amazing PowerPoint video, whatever you would like to call it, on ionization energy. So I hope you enjoyed and we get a good grade on this. So thanks for watching.